we scientists usually worry that there's a Nobel Prize winner in the room. So we're trying to describe how the Whau River and its catchment fits into that overall picture. So this is intended to give you a bit of context, if you like, for the rest of the day's proceedings. So we're going to talk about tidal creeks, where the Whau drains into the Middle Wairarapa Harbour at its base, and a couple of New Zealand ones there. This is from the Kaipara here. This is the Hokio River that drains into the Kaipara. And just to convince you, here's an aerial shot of the Whau. And if you compare it to those pictures, it does indeed look very much like tidal creeks all around the world. Now, it's not the only tidal creek that drains into the Wairarapa Harbour. So around the upper and the central parts, there are 8 major tidal creeks that drain. And they are significant because, to a very large extent, all of the fresh water and all of the contaminants that are carried in fresh water drain through those tidal creeks on their way into the larger estuary proper. Sediments, like contaminants, bugs, nutrients and so on. And we can view these tidal creeks really as the crucial connections between the land and the sea. Now, I'm not going to show too much data, but don't panic. Can you hear me okay if I kind of walk over here a bit?
Yeah.
Yeah, we're good. Okay. So what I'm showing here on the left is some data from Henderson Creek. Now, this experiment, what we had a station up by State Highway 16 measuring, and we also had a station down by the bottom. And I just want to show you a little bit of data here to make this point that tidal creeks flush contaminants out into the wider harbour. So down here is the tide going up, tide going down, and we've just got a couple of days here. This is the cumulative rainfall that's falling on the catchment. What happened over about 12 hours, we had 80 millimetres of rain falling in the catchment. And here's the point I want to make here. This shows the salinity measured at the top of the creek and also at the bottom of the creek. And if you look at low tide here, you can see that the salinity at both ends of the creek drops to 0. And what that means is that Henderson Creek at that point is functioning as a river. It's full of fresh water. It's turned from being a salty tidal creek literally into a freshwater river. And when it does that, everything that it's carrying in the way of fresh water, of course, but also all the contaminants that it's carrying gets discharged directly out into the harbour. You can also see that at high tide, the typical longitudinal salinity gradient re-establishes, so it's slightly fresher at the top compared to saltier down the bottom. Again, next low tide, it's just pumping everything directly out into the central Wairarapa Harbour. Now, as contaminants transit the tidal creek, they undergo different kinds of transformations, and this can be quite significant. This shows a picture of sediment aggregates or flocculates, if you like. It's highly magnified, so it's 8 millimetres across there, 5 millimetres across there. It's essentially a little collection of platelets. There's a lot of water in between. Now, this turns out to be significant for a couple of reasons. First of all, it affects the physical character of the sediments, so it affects the way they settle onto the bottom, and it also has an influence on the ecological effects once it gets to the bottom. And it also has an effect on other contaminants in the water. So heavy metals, for instance, they tend to leave the catchment in solution. When they reach this mixing zone of the tidal creek, they come out of solution and they attach to aggregates like that. So there are physical and chemical processes going on in these tidal creeks that transform the contaminants, and that affects the fate and effects of those contaminants. Now, the other thing that tidal creeks do is they actively sequester contaminants as well. Not sure how well you can see this, but this is a good example of this. This is the Kaipara River. So up the top there, it's leaving the south part of the Kaipara Harbour. It flows down here past Helensville. And what you maybe can see is that the water's very dirty around Helensville, which is called the turbidity maximum. It's much dirtier than the water this side, and it's also much dirtier than the water that side. There's a lot of processes that actively sustain that turbidity maximum. And again, the significance of this is that all of the dirt and mud and contaminants and so forth that are held up in that turbidity maximum are not getting out into the central part of the harbour where they would have more widespread ecological effects. So this is a significant physical feature of tidal creeks. Here's another way tidal creeks sequester contaminants. Here we are, the western edge of Central Waimata Harbour. We've made measurements out there, and what we find is that when it's really windy from the east and the northeast like today, we get lots of waves that break along this shoreline here, this Poland Island here. When they scour the bed sediments of fine sediment, it gets very dirty, the water. But what happens to that dirt, once it gets in suspension, it gets carried by the tidal currents up into these tidal creeks. At high tide, that material settles out in the mangroves, for instance, and when the tide turns, it doesn't resuspend and carry it back out. So what's happening here is that sediment is getting pumped up into the upper reaches of those tidal creeks. It's been sequestered and trapped and removed from the larger estuarine system. So you can think of those little waves, although it does make it look really dirty. In fact, what they're doing is cleansing these sandy habitats of that fine material and any contaminants that's attached out there. Okay, so let's look at contaminants in estuaries. There is a lot of bad news here. You've probably all seen it before, but I'll just repeat it. This is a summary of that bad news, if you like. We know that slugs of fine sediment that deposits in the aftermath of individual rainstorms can literally smell. Shellfish beds, for example. Chemically, it's quite distinct, and it can also form quite a thick layer. We know that agricultural runoff in terms of nutrients and fecal coliforms and so forth are having effects, in this case, algae blooms. I know there's a picture of a lake that does happen in estuaries. Heavy metals in stormwater runoff. Mangroves are spreading, and part of the reason for that is that the extra sediments depositing in estuaries are creating enlarged areas of intertidal flat, which is suitable habitat for the mangroves, in effect. We're seeing burial of otherwise sandy habitats by mud, and we also see excessively turbid water, which has a number of effects. For one thing, it can reduce the visual clarity, which affects the way visual predators live, that's fish and birds. It also has direct effects on aesthetics and so forth. It can also affect light penetration, therefore primary producers like seagrass, for example. All right. So let's look at the contaminant status of the Whau itself. This shows Auckland Council data metal concentrations in parts of the Whau, and the circle there is proportional to the concentration, and the circles are coloured according to where they fall on the guideline concentrations. These are a set of concentrations which essentially are indicative of the effects they're having on the ecology. So green and blue are not too bad. Yellow starting to want to pay attention to things. Orange and red, you do need to pay attention to things. What we see in the Whau as far as zinc goes is a number of yellow circles. Copper in the upper, more sheltered reaches of the tidal creek. We've got the yellow circles, blue out towards the mouth there. And lead, which is an interesting story, looks much the same as copper. I think the real story here comes in the way on the trend. We're looking at the zinc in the up, well, all across the Whau there, the trend is up, but it's a greater rate of increase in the upper reaches. And again, this is because it's quite a sheltered settling zone that sequesters a lot of the sediments and metals. So you can see that quite clearly here. Very similar kind of thing with the copper. The interesting story is the lead, where lead is going down. It has been for a number of years now, and the reason for that is that lead was removed from fuel.
Speak a bit closer to the green bar.
Oh, great, thanks. Is that lead was removed from fuel some years back, which is kind of interesting because it tells you that it is in fact possible to turn these trends around. It's not a hopeless case. Now, if we look at water quality, there's pretty much mixed data here. In fact, this is a number of water quality parameters. So the top two relate to sediments, so that's turbidity and suspended solids. The next three here, nitrate, ammonia, and phosphorus, and then we've got dissolved oxygen, fecal coliforms, and enterococci. The Whau here is always the last data point on the graph, coloured in red, and what this graph compares it to is water quality in different parts of the middle and the upper Waimata Harbour. I think the message to take there is that it's not doing too badly, and there are other parts, particularly the upper part of the harbour. I know you can't read this, but the largest bars there are associated with the Rangitikuni and Brigham's Creek, for example.
Sorry, where?
Rangitikuni and Brigham's Creek in the upper part of the upper harbour. And if we look at, wrong way, I'll get that right in a minute. Water quality trends, again, it's a little hard to say. That data covers 1998 to 2008. I guess what you can say about suspended solids is that maybe it's trending downwards a little bit. Nitrate, phosphorus, maybe there are fewer large peaks in runoff. You probably have to say the interclocki is about stable. It is probably fairly short time series to be making conclusions conclusively about where those trends are headed, I'd have to say. If we look at the ecological health of the benefit communities, this again is it's an index, if you like, of the overall quality or health of the benefit community. I can't really explain that to you, but there is an ecologist in the audience who can explain that to you if you really want to know. Suffice it to say, it's an indicator of the overall health of those communities. What we don't want to see are red circles there, and we do see red circles, particularly in the upper reaches of the Whau. And this is typical of this kind of environment. We have quite a strong longitudinal gradient down the creek now into the harbour. So that's a fairly indicative picture. Now, the Whau is connected to the rest of the harbour, and this is significant. It itself is a source of contaminants to the wider matter harbour, and this shows something of how that works. So if we look, first of all, let's look at sediment up here. I'm not sure whether you can read this. I'll talk you through it. The number 30% there means that of all the sediment that's deposited off Holland Island, 30% of it comes from the Whau River and its catchment. If you look up towards the northwest there, 15% of everything that's deposited there comes from the Whau. The rest of it comes from Henderson Creek by and large. That is the major source of contaminants in the harbour. And it also goes quite far afield. So that number up there in Shoal Bay is 8%, meaning that 8% of everything deposited in Shoal Bay comes from the Whau. It's a little more exaggerated even with zinc, and you can see here that that number is now 43%, 35% up here, and interestingly 11% of all the zinc that gets deposited in Shoal Bay also comes from the Whau. And you see a similar kind of picture for copper. So the message there is that this system is acting as a source of contaminants for the whole wider area. The annual average sedimentation rate, now these are averages from a number of North Island estuaries. So for instance, this red block there is from the Kaipara, and what's that saying is that the annual average sedimentation rate averaged over the whole Kaipara harbour is 7 millimetres per year. You can see the central Waitemata harbour down here at about 3 to 4. Some of these Auckland East Coast estuaries are around 5, but the real question here is how big are these numbers? We do know that the pre-catchment deforestation annual average sedimentation rate was around 1 millimetre per year, down to 0.1 of a millimetre per year, and probably more down towards that 0.1 number. So the background, or the natural sedimentation rate, if you like, is actually kind of down here, way down here, and that should give you a bit of an understanding of the scale of the problem here, a bit of a feel for how much sediments are depositing in these systems. Yep. Right. Now, most of that sediment comes in the way of mud. And I mentioned that before, that one of the main issues here is burial by mud of previously sandy habitats. And what you see here is a map of sediment texture. So those black circles indicate the percentage of the sediment that's due to mud. So 90% is the biggest circle there. We do see a lot of mud in these upper reaches, and one of the reasons, as I said before, is that these areas do tend to sequester fine sediments by those processes that I said. But the danger signal here is when you see that mud propagating out of the tidal creek and into the main harbour. So This kind of dot here is a danger signal because you see it propagating out. Possibly also out here and around here. So there are areas of the wider harbour that are becoming quite muddy quite quickly. And that's the sign that, like I said, the mud signature is coming out of these tidal creeks and into the main harbour. I won't worry about that. Talk about metals. Again, here we see ecological health of the whole harbour, which puts into context where the Whau sits here. So we've got our red dots in the Whau there, in the Henderson, Motions and Neola. Also a little alarmingly in the top of Shoal Bay there as well. It is interesting that we've got green dots along the western edge of the harbour here, and part of that is due to that physical process of waves scouring those intertidal flats of the contaminants and pushing them back up and sequestering them in the intertidal flats. So to some extent, the physical processes are acting to keep that part of the harbour clean. What does the future hold? Well, we know two things are going to happen. One is, as we continue urbanisation and we build our driveways and tend our gardens and so forth, that sediment inputs will in fact reduce. But as we build more houses and we have more cars and so forth, metal runoff is also going to increase at the same time. Now, the way those things are going to play out could be quite different in different parts of the harbour. We expect that changes in sedimentation rate over the next 50 to 100 years will be different depending on where you are. In some parts of the harbour, our models suggest that, in fact, they might turn erosional, so where previously sediments have been depositing, when we switch off those sediment supplies, that they might go back to being erosional states. But we also expect tidal creeks like the Whau will continue to accrete sediments and contaminants at much the same rate, largely just because of physically what they are. And when you translate that into metal concentrations, for instance. This is the state of the world that we predict 100 years from now, which is a pretty bold prediction. But again, we're predicting that in the central parts of the harbour, with the shutdown in the sediments, that metal concentrations might come under control. But all of the areas coloured red around here, we predict that those metal concentrations under current conditions will continue to increase. The other thing we know is that tidal creeks are very likely to change the way they behave in the future. For one thing, with more rainfall, more intense rainstorms and so forth, we expect they'll become more efficient at flushing contaminants out into the wider system. On the other hand, if we get stronger, more easterly winds, for instance, waves might become more efficient at scouring those intertidal flats and keeping them clean. We also expect with sea level rise that the basic way mixing between the saltwater and the freshwater goes on in that tidal creek will change as well. So we're looking at a number of quite significant physical changes under climate change, which will have an effect on fatal effects of contaminants and the ecological response to that. So that does bring me to the end, and I guess the conclusion here is what happens in the Whau does not stay in the Whau. This is a source of contaminants for the wider system, but it also means that mitigation, remediation and so forth that goes on here actually has the potential to deliver benefits to the wider system as well. So I'm happy to take any questions. Thanks.
Plenty of time for questions and answers, and after we've heard the first round of speakers, I don't want to do a spoiler